SwayamPrabha. Digital India. Educated India.
Welcome. So, in this lecture what I planned is just to discuss some problems. So, in this case mainly we'll look after some analytical problems basically in finite element. Means even though finite element is an approximation, so some problems we'll discuss, but the main issue for this numerical problem is this mostly numerical problems are solved in a computer. So, it is not meant for by hand calculation. So, nowadays the availability of computer and availability of different softwares and programming languages, you can code finite element in any of the programming languages, and practically speaking you learn the subject much more thoroughly or deeply if you able to code it or if you run it on a computer. So, any of the programming language what is available you can use, but I will just discuss some of the problems which are not I will not obviously calculate in terms of some numerical values. Rather, I will prefer to say the mechanics, associated mechanics and the procedure of the problem mainly. So, first thing that we discuss is this, that suppose there is a cantilevered bar. So, in this problem let us take little bit of complicated structure so that at least we can solve it. So, suppose there is a roller here and then there is a spring, linear spring at the free end. So, the spring stiffness is K and there is also a load, let us assume it Q0 is the load intensity, and then let us also assume some force which is say F0. So, and let us also assume some moment acting here, so which is M0. So, now if you want to find out the deflection of this structure, then how you will proceed. So, the inputs what you need, let us consider this is a length L and this is also length L. So, I discussed one of such problem while doing bar problem. So, naturally the free body diagram if you draw, that will give a reaction, the spring, linear spring will give a reaction here. The force that will exert or it will resist essentially is P into the K into the displacement at this point. So, that is a boundary condition here. Essentially what we need is the Young's modulus of the problem and the moment of inertia, that is I. And the procedure is very simple, what we have discussed in the previous class, that or even for the bar problem. So, let us consider two simple elements to find out the two simple elements. So, let us first know what are the degrees of freedom associated in this structure. So, this is a roller. So, here there is a spring. So, now let us consider two elements. So, this is element number 1, this is element number 2. Now, the node number 1, node number 2, node number 3. Now, what are the degrees of freedom associated here? So, here there is a displacement degrees of freedom, here there is a rotational degrees of freedom, here also you have displacement degrees of freedom and rotational degrees of freedom. Similarly, here there is a displacement degrees of freedom and rotational degrees of freedom. So, now if I denote it as W1, theta 1, W2 and theta 2 and W3 and theta 3, then the first job is to compute the elemental stiffness matrix, which we know from our previous class, that is the element stiffness matrix is this. Now, this is my element stiffness matrix where E is my element number. Now, if I write it again, so this is 2EI by L cube. Since the length of each element I have taken L for simplicity. Now, this element stiffness matrix we know. So, this is 6 minus 3L, then this is minus 6, then this is minus 3L, and then this is 2L square, then this is 3L, this is L square, then this is symmetric essentially. So, this is 6 and then again it is 3L and this is 2L square. So, this is my element stiffness matrix general form. So, what you need, EI is given, L is given, and so you can compute the stiffness matrix of the element. Now, you have also an UDL. So you have a UDL, or the distributed load is as essentially a body force term in the differential equation. So, we have to consider it domain integral, or the integral over the domain. So, here the intensity of the UDL is Q0. So, I can compute the global force vector, my elemental body force vector. Likewise, I calculated in the previous class. So, we all know about the how to compute it. So, that is Q 0 by 12. So, this is 6 minus L, then 6, then L. So, this is my body force term, and also we have the reaction terms. For instance, we will have the support moments and the shear force, which are the primary quantities here, or the force and moments or generalized force. So, we will have QE vector also. So, where generally in general terms I write it QE1, QE2, QE3 and QE4. So, QE4. So, first and third quantity is shear force, second and fourth quantity is the moment. Now, my generalized displacement, that is your U here, let me write out in this framework that UE, that is W of E, or let me write for element 1. So, for element 1, W1 theta 1, W2 theta 2, and for element 3, element 2 similarly. So, this is the overall quantities which we required. So, the quantities that we don't know involves these quantities, some of these quantities and some of these quantities, and we also know the equilibrium equation, elemental equilibrium rather I would say, that is Ke into if UE equals to your Fe and plus QE. That is my elemental equation. Now we have to assemble it for 2 elements, and since this is a beam element or essentially one dimensional element, 1D problem, so we can just assemble the some global stiffness matrix very easily. So global stiffness matrix will look like this. So Kg, so I can take you see the length is very much same, and if I take EI as constant, so over for 2 element, then I can take this quantity out, 2 EI by L cube, or rather let me okay, fine. So now if I write it, then this is 6 minus 3L, then minus 6, then minus 3L, then this is 2L square, 3L, L square, then 6, then 3L and 2L square. This is the contribution from the first element. Then we'll have the contribution from the second element. So second element contribution I can also write like this, plus 6, then this will be minus 3L, then you will have minus 6, then minus 3L, then this is symmetric obviously. So then you will have 2L square plus 2L square, then you will have this quantity, that is 3L, and then L square, then you will have 6, the other terms, so 6 and 3L, and then you will have 2L square. So this is my global stiffness matrix. So this global stiffness matrix, if you look carefully, that you have totally 6 degrees of freedom from element to element. So this matrix is 6 by 6. So if you look at the other terms, this is a symmetric matrix because the addition of two symmetric assembling of two symmetric matrix is essentially symmetric here. So now I can put these zeros because these quantities are essentially zeros. Okay, so let me write it a little bit. Yeah, so this is 0 and this is also 0. So you see, you can observe the banded structure of the finite element assembling here. So now once you are done with this, then obviously your degrees of freedom, that Kg into your global stiffness matrix, so that is global stiffness matrix multiplied by your associated degrees of freedom. So W1 theta 1, W2 theta 2, W3 theta 3. So these are my unknowns, and now you will have the global force vector. So the global force vector, if I take this thing out, Q0L, then by 12. So let me assemble it from the general assembly. So 6 minus L will be there, then 6 plus 6 will be there, then L minus L will be there, then 6, then L. So this is my global force vector, global body force vector. Then we'll also have the reaction vector or reaction force vector, that is your Q from element 1, 1, Q from element 1, 2, 1, 2, then Q from element 1, 3, Q from element 1, 4, and then we will have from the second element you will have Q 2 from shear force or the force 1, and then Q2 2, then Q2 3, Q2 4. So this is my global force vector. So this is my global force vector. Now if you look carefully from the problem, that what are the degrees of freedom is known to me and what are the degrees of freedom are known to me. And similarly, if you look carefully, the degrees of freedom which are known to me, there I don't know the reactive forces or reactive moments, that is the generalized forces. So now these degrees of freedom, that is this end is a fixed end, so W1 is 0 and theta 1 is 0. So this quantity goes to 0, this quantity is also 0. Now similarly, W2 displacement there is also 0. So and so you have three W1, theta 1 and W2 that is all 0. So you have only 3 degrees of freedom that is unknown, that is theta 2, W3 and theta 3. Now similarly, you will see that since there is a restrainment in the rotation and displacement, so there will be a force and moment generated. So these quantities we don't know, right, and these quantities we don't know, because these quantities are not necessarily 0. So we don't know these quantities. Now this quantity Q3 plus Q2, this is associated with your force, that is reaction force. So that is also not known to you. And then Q14 and Q22, that is not restrained against rotation. So rotation can happen. So there is an applied moment there. So if you look the problem, so there is a so Q Q2, if you look, that is there is a applied moment here at the roller point or the end point of element 2. So end point of element 1. So naturally that moment, the sum of these two moments that is coming from element 1 and element 2 has to be 0. So that is equals to minus m0. That is the moment, the resultant moment has to be m0. And then you have Q4, which means Q23, that is the reaction force here. So that is also given to you, but that force is essentially here is the degrees of freedom associated with that point. So essentially here that reaction force will be your F0 is the vertical force, and there will be K is the spring stiffness, and then that will be multiplied by W3. So that is your reaction force. So now this quantity should be your this F0 minus K of W3. So now, and Q24 is also 0. So there is no moment applied, and so it is free to rotate also. So the that is your equation. So if you look carefully, that you don't have 3 degrees of freedom, that is theta 2, W3 and theta 3 known. So these are my unknowns, and similarly 3 reactive forces are unknown to me. The reaction at these 2 points and 1 reaction here, the same way that we did it for the structural analysis. Now here once I implement this, that means when I include this boundary condition in the this global equation, then what will happen? Okay, there is one more thing, that is here there is no distributed load in the second element. So these quantities will be 0. So this quantity will not be there. So this distributed element will not be there. So these quantities will not be there, because these quantities will be 0. So because there is no associated force here. So Now there is no distributed out of the body force at the element 2. So now once we substitute this, then what it will take shape, I will have only these three components of the stiffness matrix, reduced stiffness matrix, and then what we'll have is something like this: 2EI by L cube, then we'll have 4L square, 3L, L square, then 6, 3L, 2L square, then you will have theta 2, W3, theta 3. This will be there, and then Q0 L by 12 into, so these three quantities will not be there because that is included in the reactions, means that will be used while computing reactions. So this now will have 3 cross 3 vectors, so L 0 0. So now you will have L 0 0, and here also you will have this three quantities which are known to me, which is M0, F0 minus KW3 and 0. So this is my final reduced equation. Now, as we have observed in case of a one of the bar problem, that this reaction is actually dependent on the displacement at this point. So obviously this will add up into the stiffness matrix. So we have to modify this stiffness matrix accordingly. So just this quantity, if I bring it here, so then it will look like this, that 2EI by L cube, then 4L square, then 3L, L square, then 6 plus your KW3. So K will be here. So if I take common, so KL cube by 2EI, that will be my stiffness contribution, and then you will have 3L and 2L square. Look, it is still symmetric because only diagonal element will be changed. So theta 2, W3 and theta 3. So now if I write this, so completely we know the right hand side, that is L 0 0, and then you will have minus M0, F0 and 0. So now you can solve this equation because you know completely this equation, this right hand side completely you know, only these three quantities and these stiffness matrix you know. So it is just linear solve. So you can solve theta 2 W3 and theta 3 to find out the two rotation and displacement. Now if you have some numerical values, you can substitute and do that, or even analytically also you can solve that. So I am just keeping that part because that part is very easy. Now the once you know these solutions, that is theta 1, theta 2, you know theta 1, theta 2, W3, theta 3, then what you can do is that you substitute these equations in this equation to compute these three reactive forces, which also you can do that because that's what we did it for structural analysis. So after substitution you can do. Now the if you want to find out suppose any moment at any point or any section, then how you can find out. So that is your that I will explain it here. So now suppose this is my original beam. Suppose I want to calculate it somewhere here, say midpoint here. Now this belongs to element 2, right? So now suppose this is at this distance is L by 2, this is also L by 2. So now here this is L. So you know the coordinate of this point. So if I take the origin here and then the coordinate of this point I know, that is x equals to L plus L by 2 or 3L by 2. So coordinate of this point. Now at 3L by x by 2 you can compute the moment. So how we can compute the moment? So suppose this is m, so we know the relation between moment and the curvature, so that is dw dx. So now from the finite element solution you know all degrees of freedom. So essentially here w is your displacement. So but displacement is actually your approximated using this. So w1 phi 1 or yes, w1 phi 1, w2 phi 2, w3, or rather let me write it in this way in an element how displacement is approximated: w1 theta 1 phi 2, w2 phi 3 and w4 phi 4. So now again this is theta theta 2. So displacement is approximated within the with the rotation. So this is your displacements. Now once you know the displacements, once you know these quantities, you can compute displacements and slopes at any point. So now first you have to recognize that this element belongs to element number 2. So naturally these calculations, your wx will be your of this form, that is w2 theta or phi 2 from element 1, then phi 2 from element 2, and then theta 2, then w3 phi 3 phi 2 theta 3 phi 2 3, and then what I mean to say is that I just wanted to mention that this is from shape functions from element 2, right? Now here if you see now theta 3, this is for element 2 deflection. So this is my deflection. Now this deflection I can easily take the derivative. So that is dw2x is essentially this 2 is from element 2. Okay, now this is dx square. Now these are constants essentially, so these are my function of x. So I can compute this w2 d2 phi 2 dx square, and then theta 2 d2 phi 2 dx square plus w3 d2 phi 3 2 dx square and theta 3 d2 phi 2 4 dx square. So phi 1, phi 2, phi 3, phi 4, we all know what are the shape functions. So this shape function is same for all element here. So this can be easily taken the derivative, and then these functions are in terms of x. So global these in terms of x bar, if you do, then this will have the x, your origin has to count from here. So if you do it in terms of x, then you have to submit x equals to 3l by 2, or if you want to do it in x bar coordinate system, you have to submit or you have to replace x equals to l by 2. So x bar equals to l by 2. So once you know this, so then you can just substitute in this equation to compute the moment at that point. No, you have to substitute x bar or x here, then you know the moment here. So that is how we calculate the moment at any point, and similarly stresses and strains, any point we can calculate. This is known as the post processing of the solution. So there is a pre-processing of the solution. So there is a, if you look any finite element software, then you will see that there is a pre-processor associated with it, and there is a post-processor associated with it. So and in between that there is a solution module. So the pre-processor is dealing with the geometry, discretization, assigning materials and all those things, and then the solution does the main solver, where you solve the system of equations essentially. It may be nonlinear, and then once you get the primary field variable, then you go for the nonlinear post-processing or computing the moments, stresses and other things. So that is known as the post-processor, where you use or even calculating the reactions. So that post-processor does all those calculations, where essentially you take the solution that you obtained from solver, and then with the known solution of the field variable, you compute the derived quantities. So this is the overall stuff I want to discuss. And then one of the problems, simple problems like this. So for instance, if you want to find out the some simple problems I will discuss. For instance, if you have the finite element, if you want to have the finite element solution of this problem, suppose there is a cantilever beam, there is an E and there is a I and there is a length L. Okay, then what is the finite element solution? Because in this case we know the exact solution of the beam problem. Then if I do it with the finite element solution, then what will be the finite element solution actually? So if I write the exact solution here, you will see that displacement is your 1 by EI for this plane, exact solution. So let me write it exact here. So here that is your minus q0 x to the power 4 by 24 plus q0 x cube by 6, then q0 L square x square by 4. So this is your exact solution. Now suppose you have a cantilever beam with a point load, okay, that is P. So in this case also we know what is the solution. So what is the exact solution? Y exact is Px square by 6 EI, then 3L minus X. Now look at those solution and finite element solutions. So in finite element solution, our approximating function, if you look carefully, that our approximating function was W or Y, whatever you say, that W was C0 plus C1 x plus C2 x square plus C3 x cube. Now this polynomial is a cubic polynomial. So now if you solve this problem with the finite element solution, the exact solution of the problem is the fourth order polynomial, while for this problem it's a third order polynomial, right, because it contains px cube term, right. So in this case what you will observe, that the second case, This is the first case and this is the second case. In the second case, you will observe that finite element solution is actually matching with the exact solution. So this is very a typical case where actually you are using same order of polynomial of the exact solution. Now in the first case, obviously if you use one element or simple two element, you will not able to match with the exact solutions. So now why the approximate solution and how the approximate solution will behave and the compared to the exact solution. Now approximate solution will mostly behave stiff way. What do you mean by stiffer way? That means the approximating displacement, or that means displacement we will get from the finite element solution will be much more higher side. So that's why in the design problem, in case of a design that is allowable, that finite element solution is useful. In that sense, it will give you the stiff solution or the stiffer solution. Now exact solution is a fourth order polynomial. Why it is happening? Because of the finite element solution, because finite element functions are cubic polynomial. Now in this cubic polynomial, it cannot approximate the all possible modes of the deflection. So that's why it gives the stiffer solution, rather the exact compared to the exact solution. While in the second case, where we are just using the point force, the approximate solution and the exact solution matches, because approximating function can catch the all modes associated with the displacement. So that's why it is very important that that how your behavior of the system. So that's why doing these problems are very important to learn the finite element, because nobody uses actually finite element for such a simple problem. The idea is to solve or use finite element where we really don't know the exact solution, or which is difficult to obtain. Maybe obtainable, but if it is for instance the previous case, the previous problem that we have discussed, it is very difficult to obtain an exact solution for that problem. So but it is possible to find out, but it is very difficult to obtain. On the other hand, finite element solutions like direct stiffness matrix that we have used is very much flexible in terms of that. So that's the idea behind using this technique. And it is applicable to higher dimension also, that we will see in this course in due time. In due course of time. So now another type of problem you may encounter, that we have also discussed in the previous lecture, that is your frequency, finding out the natural frequency of a structure. For instance, if I want to find out the natural frequency of a simply supported beam, so the simply supported beam, you know the associated mass and the stiffness matrix. So suppose we discretize with two element 1 and 2, then your elemental equilibrium equation is essentially Ke minus omega square Me. So this multiplied by your degrees of freedom, that is your UV equals to 0. So this is your essentially the eigenvalue problem, where omega is the natural frequency. So now to find out the natural frequency of the system, you have to just do the same procedure and the finding out the solve the eigenvalue problem to get the first natural frequency. So in the any case, for instance, if I tell you the finding out the first natural frequency of the previous problem that we have solved, it is very difficult to obtain. But with the finite element, or with the finite number of approximations, we can actually compute it very easily. And the more important thing, we can actually compute it in a desktop computer or any other computer, so with the help of any programming language. So I'm not just doing this problem in detail because this is a very simple problem. So another thing I just wanted to point out is for instance, we the Hermite polynomial that we are using for finite element shape functions. The main difference between the Lagrange and the Hermite polynomial here is that in the Hermite polynomial we need the derivative continuity because the theory requires us, means theory required that. So that's why means we not only need the continuity of the displacement, we also need the continuity of the first derivative or the slopes. So that is your dw dx. So this this requirement poses the Hermite type of shape functions. And suppose even though it is not required, because bilinear form doesn't want, okay, so if I need my second derivative continuous, for instance the curvature, d2w by dx2 is the curvature. Now if I want the curvature to be continued, then I can also devise a beam element which will have 3 degrees of freedom per node. For instance, if I devise an element something like this, even though these are not standard elements, so these are my w1, theta 1 and kappa 1. These are my 3 degrees of freedom at each node. So I can also formulate an element which involves this kappa is essentially the curvature vector. Now or curvature at a point. So now this also can be found out. For instance, you have now 3 degrees of freedom per node. So obviously you have 3 such conditions. So you need 6, you can evaluate 6 constant uniquely, right? Because you have 6 boundary conditions or the 6 conditions, you have to have 6 unknowns to find out the unique solution. So in that case I can always write my polynomial, higher order polynomial, for instance c1x c2x squared plus c 3x cube and c4 x to the power 4 and c5 x to the power 5. So you see I have 6 such constants. So I can always, and I need dw dx and d2w dx to be continuous. So with these 3 conditions I can always find out my shape functions for this element. So similarly, this is one possibility. Another possibility is I can consider 2-noded, instead of 2-noded beam element I can also consider 3-noded beam element. For instance, if I consider this element where I don't have like quadratic Lagrange polynomial or quadratic shape functions, I can also have my 3 nodes. Suppose I have a middle node here, so then I can also consider the same function and only use the first order derivative continuity. That means I have w1 theta 1 here, w2 theta 2, w3 theta 3, 1 2 3. So this is 3-noded beam element. So in this beam element I can also use the same shape functions because I have I have 6 such conditions. So 6 such generalized displacement. So I will use the same shape functions, that is c0 plus c1x plus c2x square plus c3x cube plus c4x to the power 4 and C5 x to the power 5. So now here I need I will satisfy only this continuity, rather the curvature continuity. Here how the sixth condition is coming out, because it is coming out from the three nodes, not because of the derivative, second derivative continuity. So this is the possibility, even though these elements are not standard elements, because we can always refine the element to increase the number of node or numerous degrees of freedom in the system. So while doing finite element solutions, you have to keep in these things in mind, that polynomial refinement or the mesh refinement, which is popularly known as the increasing the number of element or increasing the degrees of freedom. So there are two possibilities. So generally mesh refinement is very much preferred, because polynomial refinement is always not useful. So that's those things we have to keep in mind, and it is very much problem dependent. It is not that it is problem independent, that you have such sub strategy which is universal for all problem. So it is for problem dependent, and for this type of problem it is generally useful to use the mesh refinement or polynomial refinement. So now these things you have to keep in mind. Now moreover, I want to reiterate what I initially stated before this lecture, that finite element solution is not for pen and paper. So it is for you to code that thing on a with the help of any computer and programming language. Then only you can learn exactly what happens, how the solution is calculated. So I suggest everyone, if you have any programming language, if you know any programming language, you can use these theories and code it in that programming language to solve simple problems, how they perform, because most of the simple problems you know the exact solution. You can compare how much element refinement is required to get this acceptable amount of accuracy with the exact solution. So that's all. I stop here. We'll meet in the next lecture or in the next class. Thank you.